This video is for BEL, showing how to cut out multiple parts and the cleanliness of the parts. It's important, however, to identify what we're doing and explain the process. This sheet has been cut multiple times. Some of the parts have been cut out completely, some have been cut out with tabs. So although pieces are located here, some of them have already gone through the cutting process. There's one area here, this top 4 rows, that have not been cut. The ones below it have. So we're going to focus on this area here. What's important to note is that we measured all the individual parts in rows 1 through 4, columns 1 through 6, and there was a variation between the size of the parts. The variation ranged as much as 40 microns in both height and width in different parts. We couldn't find any consistency between the rows and the columns. It seemed to be a completely random pattern as far as different sizes. But we will show you the spreadsheet on that, on the analysis on how that came about. So we put the sheet on our coordinate measuring machine, and Greg put in a program to measure each individual part in that array of 24 parts. So go ahead and hit click. You can see that the machine is measuring the external dimensions, rectangular dimensions of each individual part. So we downloaded all the information, all the measurements from the coordinate measuring machine into a spreadsheet and identified the parts as part 1 through 24. Part 1 would have been the part in the uppermost left-hand corner, then going across row 1 through column 6 would have been part 6. The second row would have been row 7, or part 7 to part 12. The third row, 13 to 18. The fourth row, 19 to 24. That we measured all the parts are identified as far as the width and the height. So the smallest numbers in width and height are in red, which was part number 6, had a width of 11 millimeters, 11.951 millimeters. It had a height of 8.909. The greatest height was part number 11, 8.936, and the greatest width was part number 17, 12.06. You can see from the graphs a pretty significant variation from the average. The range varied by 55 microns on width and 27 microns on height. So to cut these parts, we need to establish what our cutting dimensions are going to be, realizing that there's going to be more or less Teflon on the different parts depending on the individual size of the part. So we decided to use a cutting dimension of 12.06 on the width and 8.96 on the height. This is a proportional increase, a percentage increase of BEL's drawing on this part. But it's important to note that the direct tolerances or range of error that we have, if you take away the cutting dimension from the average of these parts, is there is more room for error, 88 microns on the width, and there's only 41 microns room for error on the height. And the beam is about 20 microns. So if you have the beam cutting top and bottom, and you only have a variation of 24 microns to play with, it's far more likely that we would be touching the copper on the top of the part as opposed to either side. There's more room on the sides for error. So when you're doing your cutting, you have to determine, based on the variety of the different sizes, what you want your cutting parameters to be. This is just the cutting parameter we picked. That's not saying you have to do it that way. It's saying this is what we picked. And all our cuts should be within a consistent range of this cutting parameter. However, because the parts vary so much, you're going to get more or less Teflon on different parts. So for example, we would expect the most Teflon to be around part number 6, which has the smallest dimensions. We would expect there to be very little Teflon on the top of part number 11, which has the highest dimension. And we would expect there to be very little Teflon on the sides of part number 17, which had the widest dimension. We redid the vacuum on it to see that if you cover up the extra holes on the outside with plastic, then the part is very secure. So the parts are loaded in the machine right now. We close safety glass. Ray's going to hit the go button. It's going to use machine vision to identify one of the lower semicircles at the bottom of the part. So the machine vision is picking up each part and then cutting each individual piece on the array of 24 parts. You can see the parts that are backlit here, other than the tabs, they're cut through. You can see the light coming through. You see where the tabs are located. Cut those with the razor blade. So we have the cut parts back in the core measure machine, and you can see from a visual display, what we did was we did additional passes, and expanded the scale so that multiple passes would go back and melt away any excess Teflon that was surrounding the edges of the parts. So we still have the tabs in place, and as you go around the part, you'll notice that it's pretty eliminates most of the Teflon touching the copper area. This is the same part under a higher magnification. You can see that there's very little Teflon, almost too little to measure, surrounding the copper area right now. This is part number 6, which I referenced earlier in the video when we were talking about the spreadsheets. This is dimensionally the smallest part in the group, and we would expect it to have the most extra Teflon in the edge, which appears to be the case. As you go around the edges, you'll definitely see a little more Teflon than some of the other parts still attached to the copper. But again, it's because the laser cut is consistent, but the part itself is an inconsistent shape from other parts. The sheet that we are working with does have the word rejected written on the top, so perhaps we have a rejected sheet that did not meet your specifications as far as size is concerned, but there was a big inconsistency between the parts. This was part number 11. We had some concerns based on the measurement that it was the tallest part, that there would be some cutting into the copper, which is just barely touching the edge on the bottom. And if you look up at the top, it's basically on the edges of the top as well. So it seemed to have worked out okay, better than I expected, but wasn't any major issue there. Last thing I want to do is measure the consistency of the cuts. So we've gone back to part number 6 here, which we talked about had a little extra Teflon on it. And I'm going to measure the width and the height of the cut on this part and then compare it to one other part, just to show that even though the parts are different sizes, the cut will be the same consistency. So I'm going to establish a line here based on where the cut is. Then I'm going to compare those two lines. And those lines are about 12.112 millimeters apart. I did the same thing for the height of the same part and came out with a difference of 9.034 for the cut of that part. So I did the measurement on the cut width for another part on the width and got 12.116 millimeters, so within 4 microns of the last one. Then I measured the difference in height of the cuts and got to 9.038. So again, within about 4 microns of the other part I measured.